Hello everyone, welcome to the video lecture series on computer organization and architecture. Our today's topic is data representation and we will discuss number systems, binary to decimal and decimal to binary number systems. So at the end of the lecture, you will be able to define number systems, base and distinguish between positional and non-positional number systems. So not only that, you will be able to explain decimal and binary number systems using positional weights for integer and fractional parts. You will be able to convert decimal number systems to binary and binary numbers to decimal for both integers and fractions. And finally, you will be able to analyze and verify mixed integer fraction conversions using appropriate step-by-step methods. So why number systems matter? Number system is a method of representing numbers using symbols and rules. So on daily life we use it for counting, arithmetic. In electronic circuit it is used for developing digital electronics, computer systems, and our today's focus is to learn how number systems are used in data representation. One thing we must note that humans commonly use the decimal number system, as we know, while computers mainly use the binary number system. So from where the journey of number systems began? So in the ancient times, early humans used tally marks, sometimes on the bones, sometimes on the stones, and they used to count the lines. Ancient civilizations such as Egyptians and Romans, they developed a bit modern symbolic systems that we know that X, V, I, such letters are used to represent numbers. However, these systems were useful for counting but not so convenient for arithmetic purpose. So the journey of decimal number systems began in ancient India around the 6th century CE. The binary number system described by Leibniz in 1703 became the foundation of modern digital electronics and computers. To make it more convenient, by grouping 3 binary digits, the octal number system was developed, and similarly in the same time by grouping 4 binary digits, the hexadecimal number systems got very popular in the year of 1950s. Now two types of number systems are there. One is non-positional number systems. So for example, I draw one line to represent 1, I draw 2 lines to represent 2. Now if I draw the second line either on the left or right, it does not matter. 2 lines means 2. Similarly, if I draw 3 lines, so it means 3. So the value of the symbol does not depend on the position of the lines that I have drawn. In contrast, positional number system, the value of a digit depends on the digit itself, its base and position of the digit. What does it mean? Suppose I write 2. Now, if I write another number 3 on the right side of 2, it becomes 23. But if I write 3 on the left side of 2, it becomes 32. So the value of the digits are depending on the digit itself. So for example, 2 and 3 are used in both the numbers, the position of the digits and the base. Now how base is useful here? Because 23, it means we know that 20 plus 3. So 20 plus 3 means 2 into 10 plus 3, or 2 into 10 to the power 1 plus 3. And 32, it means 3 into 10 to the power 1 plus 2. So in the both cases, the value is depending on the digit itself. It is depending on 3, it is depending on 2, and the base is 10, and based on the position the power of 10 is decided. So positions means, for example, if we take 32, so the position of 2 is called 0th position and position of 3 is the first position. So that is why 3 into 10 to the power 1 is the position of that place, and 2 into 10 to the power 0 actually. Okay, so that is why in positional number systems the value of a digit depends on these 3 factors. Now for binary systems, the base is 2, the allowed digits are 0 and 1. For octal, the base is 8 and the allowed digits are 0 to 7. For decimal, the base is 7 and the allowed digits are 0 to 9. And for hexadecimal, the base is 16 and the allowed digits are 0 to 9 and A, B, C, D, E, F. So A, B, C, D, E, F is nothing but 10, 11, 12, 13, 14, 15. So we will discuss later about hexadecimal, octal, these 2 number systems. So today's focus is only binary and decimal. So let us take one example of decimal integer. So 234. 234, we can write 234 as 200 plus 30 plus 4. So 200 can be expanded as 2 into 10 square plus 3 into 10 to the power 1 plus 4 into 10 to the power 0. We can expand in that way. So from this expansion we can come into conclusion that the decimal number system has a base 10 because each of the terms we can express as a base of 10. It is using 0 to 9. The digits are 0 to 9 because 2, 3 and 4, these are the digits that falls in the range 0 to 9, and as 234 is an integer number, so each of the digits are actually using the positive power of 10. So for this position the power is 2, for this position the power is 1, and for this position the power is 0. So in that way we can expand one decimal integer. Now what about for decimal fraction? So decimal fraction means fraction part will be using negative powers of 10. So 0.67, it means that 6 into 10 to the power minus 1 plus 7 into 10 to the power minus 2. Why is it so? Because 0.67 means 0.6 plus 0.07. So 0.6 means 6 into 10 to the power minus 1, and 0.07 means 7 into 10 to the power minus 2. So for decimal fractions, the fraction part uses negative power of 10. Now come to decimal to binary conversions. So we will learn how to do that through the steps that have been given here. So first we will write the number that is given. So for example 25. So we will divide the number by 2 as per step 1. So we will divide. So what will be the quotient? The quotient will be 12, and we will keep track of the remainders. So in this step the remainder is 1. So remainder is recorded. Then again I need to divide it by 2. So 6 is the quotient, and definitely the remainder is 0. Again I need to divide it by 2. So 3 is the quotient and remainder is 0. Again I divide by 2. This time the quotient is 1 and remainder is also 1. Now if I try dividing 1 by 2, as 1 is less than 2, so my quotient will be 0 and the remainder will become 1. So finally I get a complete record of remainders. Now what to do? This step is very crucial. Now I need to keep record of all remainders from bottom to top in this direction. Please remember this direction, bottom to top. So if I go bottom to top, then what I am seeing, the number is 11001. This number is a binary number, and please don't forget to mention its base. So you need to write the base is 2. Okay, so in this way we can convert a decimal integer to a binary integer. Now how to convert a decimal fraction to a binary fraction? So for that we need to make one table. How does it look like? So first we will write fraction into 2. This is my first column of the table. Second is so if we multiply the fraction, that is given fraction, for example 0.625, definitely we will get some result. So this is the fraction part of that result. So fraction part of the result. Now that result may contain some integer part. So this is the integer part of the result. So integer part of result. So in this way we will make a 3-column table and we will start the operation. So first step is, what is the given fraction? 0.625. So 0.625 into 2. What will be the result? 0.625 into 2. So the result will be 1.25, right? So 0.625 is equal to 1.25. Now what will be the fraction part? Definitely 0.25 is the fraction part. And what is the integer part? Definitely 1 is the integer part. Okay. Now what we will do, whatever is the fraction part, we will bring this fraction part to the second step. So now my fraction is 0.25 and we need to multiply by 2. So 0.25 into 2 means 0.5. This is my result at this step. So 0.5 means what is the fraction part of the result? 0.5. This is my fraction part of the result. What is the integer part? The result is itself 0.5. So definitely the integer part is 0 here. So now I will again bring this fraction into the third step. So 0.5 into 2 is equal to 1.0. So 1.0 means the fraction part is 0 here and the integer part is 1 here. Now at this step we need to stop, because if we bring this 0 to the next step, actually we won't get any result. So we stop here. This process is stopped here. Now it is very crucial to note that we need to record this integer part of the result from top to bottom. Please note that this is different from the integer part. So for integer, what we did, we recorded the numbers from bottom to top. Can you see that? But this time we are recording the number from top to bottom. Now by chance the result is 101 here, so you will be getting the same number even if you go bottom to top by mistake, but please remember that all the time you need to go from top to bottom. So anyways, so in binary the result is 0.101 and you need to mention the base. So following the steps, you can try with any fraction and you can also get the result. Now let us try one combination, because we have learned that how to convert a decimal integer into binary, and also we have learned how to convert one fraction decimal into binary. Okay, so whenever such problems are given, for example 18.375, so we will do this separately. So first we will make it for integer part. So we know that what to do. So for integer part, we take the number 18, we divide by 2, so the quotient is 9, the remainder is 0. Again we divide, the quotient is 4, the remainder is 1. We continue, so quotient is 2, remainder is 0. Again, the quotient is 1 and remainder is 0. Again we should try dividing 1 by 2. So definitely the quotient will be 0 this time, because 1 is less than 2 and the remainder is 1 itself. So now we get the complete set of the remainders collected from this division process. Now for integer, we will go from bottom to top and our result will be 1 0 0 1 0. Please indicate the base of binary. Now for the fraction part, what to do? So we will make these 3 columns like fraction into 2, then fraction part and integer part, just like we did integer part. So the given fraction is 0.375. So 0.375 into 2 is equal to 0.75. So 0.75 is the fraction part and integer part is 0. So this 0.75 will come here. So now we will make 0.75 into 2. So the result is 1.5. So the fraction part is 0.5 here and the integer is 1. So now the 0.5 will come here. So 0.5 into 2 is equal to 1. So the fraction part is 0 definitely, because 1 means 1.0 and the integer part is 1. So now the fraction part is 0. So if I bring it to the next step, so going forward it will be all 0. So anyways, we have collected these integer parts from this operation and we will collect it from top to bottom this time. So if I collect it top to bottom, then the result will be 0.011 in binary. So what will be our final answer? So final answer would be, we need to combine this integer and fraction parts. So our result will be 1. So first we will write the integer part that we have obtained 1 0 0 1 0 point 0 1 1. So this is our final result. Now you also can try different types of numbers that are combined form of integer and fractions, and you can also practice. Now let us learn that how to convert binary to decimal. So binary to decimal conversion starts with counting the number of bits. So for example, in the given problem, it is 1 1 0 0 1, right? So first we will count the number of bits. So how many bits are there? 1 2 3 4 5 bits are there. Now as 5 bits are there, so we can say that this is position 0, this is position 1, this is position 2, this is position 3, and this is position 4, sorry. Okay, so that is why if the total number of bits are n, so the position is actually 0 to n minus 1. So this needs to be very clear first. So when the position have been obtained, then what we will do, we know that the base of decimal is 2. So that is why we need to write proportional weights for the bits. Okay, so weight means just like in the decimal, for example 234, this example we have taken. So what we did, we multiplied 2 with 10 square, 3 with 10 to the power 1, and 4 with 10 to the power 0. So this 10 square, 10 to the power 1 and 10 to the power 0 are actually called the weights of the position. Okay. Now similarly for binary also, the weights needs to be calculated, but this time as the base is 2, so the weights will look like this. So the weight for this fourth position will be actually 2 to the power 4. The weight for this position, next position is 2 to the power 3. Next is 2 to the power 2. Next is 2 to the power 1, and the rightmost one is 2 to the power 0, right? So what we can write? We can write 1 into 2 to the power 4. So we have multiplied this digit with the corresponding weight. Then 1 into 2 to the power 3. Then the next digit is 0. So actually this is 0 into 2 to the power 2. So I am writing for your convenience. Ultimately it will be 0. However, so 0 into 2 to the power 1, and finally 1 into 2 to the power 0. So we can expand in that way. So we know that 1 into 2 to the power 4, 2 to the power 4 means 16. So 16 plus 2 to the power 3 means 8, plus 0 plus 0 plus 1 into 2 to the power 0. So 2 to the power 0 means 1. So 1 into 1 means 1. Always remember, something to the power 0 is always 1. So 16 plus 8 plus 0 plus 1. Finally, this is 25, and definitely you need to write the base of the decimal number, that is 10. Okay. So following these steps, you can also try with any binary number and convert it to decimal. Now let us try with fraction. So how to convert a fraction, binary fraction, into decimal fraction? So 0.101. So it will be done in the similar manner, 101. So here, what will be the weight of this position? 2 to the power minus 1. For this, the weight of the position is 2 to the power minus 2, and for this position the weight is 2 to the power minus 3. Okay. So if I expand, so the digit multiplied by its weight, so 1 into 2 to the power minus 1 plus 0 into 2 to the power minus 2 plus 1 into 2 to the power minus 3. So 2 to the power minus 1 means half. So this is 0.5 plus 0, and 2 to the power minus 3. 2 to the power minus 3 means 1 by 8. 1 by 8 means 0.125. So if I add, then it will be 0.625, and this will be your decimal fraction. Don't forget to write the base. Now let us try one combined integer and fraction. So here we will compute separately. So first for integer. So for integer, this is 101. So as we discussed, first you need to count the number of bits. So 3 number of bits are there. So for here n is 3. So the range of the positions will be 0 to n minus 1. It means 0 to 2. So this will be having the weight of 2 to the power 0. This will be having the weight of 2 to the power 1, and this bit will be having the weight of 2 to the power 2. So what will be the final result? 1 into 2 square plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So this will be 4 plus 0 plus 1 into 2 to the power 0. 2 to the power 0 means 1. So 1, it means 5, and base is 10. Now what will be for the fraction part? So I am writing the fraction part here. So for the fraction part, it is 0.01. So this will be equal to 0 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 is equal to 0 plus 2 to the power minus 2. It means 1 by 4 So 1 into 2 to the power minus 2, it means 0.25. So 0.25, this is my decimal fraction. So if I combine these two results, so the final answer will be 5.25. This is in decimal. Okay. So in this way, you can convert any binary number, be it in integer or fraction or any combined form, to the decimal number. So in this lecture, we introduce the concept, the history and importance of number systems, and then we explain the decimal and binary number systems using positional notation and the powers of the base. And finally, after demonstrating step-by-step conversion, we extended the conversion methods to fraction and combined numbers containing both integer and fractional parts. So thank you everyone for listening to this lecture. So in the next lecture, we will be covering the other number systems. Thank you.